When adversaries breach an organization, they rarely linger on the periphery. Their ultimate target is the database, the repository holding the most sensitive, core assets an enterprise possesses. Relying solely on network perimeter defenses like firewalls leaves a massive architectural blind spot. Once an attacker navigates past that outer boundary, the inner data layer is often entirely exposed. Effective defense requires moving past network routing. We have to systematically audit the specific architecture and configuration of the database engine itself. This requires a comprehensive database security assessment. It is a precise evaluation designed to uncover vulnerabilities and misconfigurations directly at the data layer before they can be exploited. The methodology works from the outside in. It starts by modeling external threats and then drills down into highly specific engine-level configuration hardening. Engine-level hardening replaces a brittle outer perimeter with a defense in-depth model, ensuring that the data core remains protected even when the network layer is compromised. The assessment begins by defining the threat simulation scope. We use 3 specific models to understand the exact vantage points an attacker might exploit. First is black box testing. This simulates an external attacker targeting the database interfaces with absolutely zero internal knowledge. The focus here is strictly on identifying exposed ports, unauthenticated endpoints, and web-based injection routes from the outside internet. Next, gray box testing simulates an attacker who has already breached the perimeter, acting as a compromised application server or a standard internal user. From this position, we look for cross-tenant data leaks and test if internal roles can escalate privileges without authorization. Finally, white box testing is a comprehensive audit performed with full database administrator access. We review underlying schemas, stored procedure source code, and precise configuration files. Layering these 3 vantage points reveals specific vulnerability pathways hidden to single-layer audits, whether the threat originates externally or from within the network. The audit then moves to the second phase, examining authentication and perimeter access. For databases hosted in cloud environments like AWS RDS or Google Cloud SQL, verifying perimeter isolation is the immediate priority. We explicitly verify that the publicly accessible flag is set to false. We then enforce IAM database authentication to eliminate the risk of compromised static passwords. Traditional relational databases require their own engine-specific authentication hardening. In Postgres configuration files, auditors must locate and eliminate weak trust or MD5 authentication methods, replacing them with stronger hash protocols. Similarly, for MySQL, we audit for strict hash complexities and explicitly disable remote root logins by binding the address locally. Strict authentication protocols ensure that unauthorized requests are dropped before they can reach the database's internal logic. Once the perimeter is secured, the assessment enters its third phase, access control and privilege hardening. Every configuration is governed by one operational concept, the principle of least privilege. Users and applications must only have the exact permissions necessary to function. When this fails, environments suffer privilege creep. Standard users accumulate unauthorized administrative permissions, creating direct pathways to critical data tables. To stop this in Microsoft SQL Server, we audit the system by reviewing memberships in the sysadmin role and locking down default administrator accounts. In PostgreSQL, the audit strips away unnecessary attributes from user roles, specifically targeting unneeded permissions to create databases or generate new roles. For NoSQL systems like MongoDB, this means ensuring that root roles are strictly confined to designated maintenance users only. Strictly enforcing least privilege guarantees that even if a single account is compromised, the attacker's blast radius is severely contained. The assessment then targets the deepest, most complex layer, engine-specific vulnerabilities and query auditing. A secure database minimizes its attack surface by actively identifying and disabling unnecessary default features. For example, in Microsoft SQL Server, administrators must locate and permanently disable dangerous extended stored procedures that could allow an attacker to execute arbitrary system commands. In MySQL, the equivalent hardening step is disabling local file privileges to block arbitrary file disclosure vulnerabilities. Beyond configuration, the database engine must parse queries. Query injection remains a constant threat, but the attack vectors vary heavily based on the specific architecture. Traditional relational databases face standard SQL injection through web applications. Modern NoSQL environments, however, are targeted through parameter manipulation. A MongoDB audit requires security teams to test REST and GraphQL parameters against complex regex injections and unauthorized query pipeline manipulations. Treating all databases as identical, monolithic systems ignores the very specific, unique architectural flaws that adversaries actively exploit. The final tier of the defense strategy establishes the ultimate fail-safes: data protection and active logging. The assessment must verify that strong encryption methods are applied to data at rest and data in transit. This requires the correct implementation of transparent data encryption for stored files, alongside strict SSL transport rules to secure the network traffic. Off-site data requires the same rigor. Automated snapshots and cross-region backups must be explicitly encrypted via cloud key vaults. Protection at rest is then paired with active monitoring through comprehensive database audit logging. These audit logs must be configured to stream directly into a centralized security information and event management system, allowing teams to detect anomalous queries immediately. Robust encryption paired with live telemetry transforms a database from a passive storage unit into an actively monitored vault. From mapping external threat models down into highly specialized engine-specific configurations, the entire architecture must be hardened. A true database security assessment functions as a structural alignment, identifying the misconfigurations and logic flaws that automated scans routinely miss. This rigorous alignment uncovers misconfigurations and eliminates zero-day bugs before bad actors can ever reach the data layer. Achieving this technical state is also how an organization proves its data security posture to external partners and auditors. Documenting this proof of security easily satisfies stringent data protection mandates, including GDPR, HIPAA, and SOC 2. The cost of post-breach incident response is catastrophic. Routine, proactive security assessments eliminate those risks before they materialize. In a shifting threat landscape, continuous database defense provides the structural stability required to maintain core operations and protect service availability.